In the deep frontier of the observable universe lies a distant cosmic anomaly, the galaxy known as HLSJ091828.6+514223, poetically termed the icy galaxy of the early cosmos. Situated approximately 13 billion light-years away, this celestial object reveals itself as it was just 700 million years after the Big Bang, a period cosmologists regard as cosmic infancy, when galaxies were expected to be primitive, metal-poor entities still assembling their first generations of stars. Yet HLSJ091828.6+514223 defies classical predictions. Rather than a simple, sparsely populated galaxy, it radiates an intense, dust-rich glow across the infrared spectrum, indicative of an abundance of heavy elements, carbon, silicon, iron, typically forged over billions of years through stellar evolution and the cataclysmic deaths of massive stars. This enrichment, normally seen in older, more mature galaxies, appears here prematurely, signaling processes at play that stretch or even challenge conventional cosmological models. Observations with advanced instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, reveal prolific star-forming activity at a rate exceeding hundreds of solar masses per year, rapidly assembling stellar populations and swiftly polluting the interstellar medium with metals and dust. Such extreme starburst conditions imply that star formation in the early universe may have proceeded at unprecedented rates, propelled perhaps by intense gas inflows or collisions with neighboring protogalaxies. One compelling explanation for this precocious metallicity and dust enrichment is the presence of a hidden active galactic nucleus, AGN, a supermassive black hole swiftly devouring surrounding gas and dust, channeling immense energy outward, and triggering explosive star formation episodes. Alternatively, theorists posit the existence of extraordinary stellar populations, massive, short-lived stars known as Population 3, that rapidly evolved, exploded as hypernovae, and seeded the galaxy's interstellar medium with vast quantities of heavy elements far sooner than previously imagined. The discovery of HLSJ091828.6+514223 offers astrophysicists an exciting challenge, forcing reconsideration of long-held assumptions regarding galaxy formation, stellar evolution, and cosmic chemical enrichment. Every data point retrieved from this enigmatic galaxy encourages theorists to revisit cosmological simulations, recalibrating star formation efficiencies and heavy element yields to accommodate the unanticipated complexity of the early universe. While classical theory might stumble at the threshold of this distant icy galaxy, modern astrophysics welcomes the mystery. By confronting such puzzling objects, researchers are not only refining their models of galaxy formation but also sharpening our fundamental understanding of how the early universe rapidly transitioned from simplicity to astounding complexity. The striking infrared brightness of HLSJ091828.6+514223 prompts astronomers to explore unconventional star formation mechanisms. It hints at the existence of hyper-efficient cooling processes, possibly driven by molecular hydrogen combined with early enrichment by heavier elements, allowing rapid fragmentation of dense molecular clouds into stellar nurseries far faster than conventional models anticipate. These clouds, rapidly collapsing under their own gravity, could trigger bursts of star formation, fueling a runaway cycle that explains the galaxy's extreme luminosity. Further spectroscopic analyses of HLSJ091828.6+514223 reveal unexpectedly high abundances of carbon monoxide and water ice grains, compounds whose presence signals intricate chemical networks at work in the early cosmos. Such complex chemistry, typically presumed to occur in mature galaxies over billions of years, presents a cosmic puzzle. How did the necessary preconditions, low temperatures and sufficient densities of heavy molecules, arise so swiftly after the Big Bang? One intriguing theory suggests the early universe hosted pockets of accelerated stellar evolution, regions where massive stars, hundreds of times the mass of our Sun, formed, burned rapidly, and exploded violently within mere million-year lifetimes. These hypernova events would eject vast quantities of synthesized heavy elements into the surrounding gas, rapidly seeding interstellar dust and ice, and thus jump-starting complex chemical pathways far earlier than standard cosmological models allow. Alternatively, theorists have considered scenarios involving intense cosmic inflows, streams of pristine hydrogen gas, channeled directly along filaments of the cosmic web toward the galaxy's gravitational center, could have triggered simultaneous bursts of star formation and black hole growth. These turbulent, high-pressure environments would compress gas clouds at unprecedented rates, sparking violent stellar births and massive chemical enrichment. Upcoming observational missions, such as the James Webb Space Telescope, JWST, promise deeper glimpses into this young cosmic oddity. High-resolution infrared spectroscopy will unlock precise insights into elemental abundances, stellar populations, and possibly direct evidence of a hidden AGN. Meanwhile, large-scale cosmological simulations incorporating non-standard stellar initial mass functions, rapid supernova feedback, and enhanced cosmic inflows are being developed to reconcile such anomalous observations with theoretical predictions. In confronting the mysteries posed by HLSJ091828.6+514223, astronomers stand at the intersection of observation and theory, pushing the boundaries of current cosmological frameworks. This distant, icy beacon from the dawn of cosmic time is more than a curiosity. It is a gateway to refining our comprehension of how galaxies, heavy elements, and even the conditions for eventual planetary systems came to exist in our complex and beautifully unpredictable universe. As researchers delve deeper into HLSJ091828.6+514223, they also begin to question fundamental assumptions about cosmic timelines. The very presence of dust and ice at such early epochs not only challenges star formation models, but also forces astronomers to reconsider how quickly the universe transitioned from a state of pristine simplicity, dominated primarily by hydrogen and helium, to one enriched with the heavier elements that later became the building blocks for planets and, eventually, life. Detailed studies of the galaxy's spectral lines suggest the dust grains themselves may differ substantially from those in modern galaxies. Some astrophysicists propose that this primordial dust might consist predominantly of larger, more resilient grains, formed rapidly from the intense ejecta of massive early stars or supernovae. This distinctive dust composition could profoundly alter our understanding of how interstellar dust influences galaxy evolution, potentially enabling faster cooling of gas clouds and thereby significantly accelerating star formation in early cosmic environments. Theoretical models are now evolving to incorporate such rapid enrichment mechanisms. Recent computational simulations of galaxy formation, integrating powerful feedback loops involving massive starbursts and active galactic nuclei, begin to approximate the rapid chemical evolution observed in HLSJ091828.6+514223. These simulations suggest a previously unrecognized interplay between early stellar populations and central supermassive black holes, rapidly recycling matter through violent winds and jets, enriching their galactic environments far faster and more extensively than previously considered plausible. Moreover, HLSJ091828.6+514223 could represent only the tip of an observational iceberg. If this galaxy's extreme evolutionary state is indicative of common processes in the distant cosmos, astronomers expect future observations, particularly from deep-field surveys using JWST, to unveil an entire class of similarly precocious galaxies lurking at the universe's edge, each challenging conventional timelines of cosmic evolution. Researchers are also eagerly anticipating improved gravitational lensing techniques to magnify even more distant, faint sources, revealing detailed physical processes within galaxies such as HLSJ091828.6+514223. By harnessing the natural gravitational lenses offered by massive galaxy clusters, astronomers hope to resolve previously hidden structures within these distant galaxies, further illuminating their enigmatic origins. Ultimately, the study of galaxies like HLSJ091828.6+514223 underscores the extraordinary richness and complexity of cosmic history. Each observation pushes astrophysics toward a more nuanced narrative, one where the universe's youth was far more dynamic, chemically diverse, and turbulent than traditional theories predict. This ongoing dialogue between observation and theory promises not just incremental refinements, but potentially paradigm-shifting leaps in our understanding of the cosmos, from the birth of the first stars to the eventual emergence of life itself. The exploration of HLSJ091828.6+514223 also shines a spotlight on another critical question: what was the exact role of dark matter in sculpting early galaxy formation and starburst conditions? This galaxy's unusual activity and enrichment might imply a remarkably dense halo of dark matter, which provided the gravitational scaffolding necessary for rapid gas accretion, intense compression, and accelerated stellar assembly. If confirmed, this would offer new constraints on models of dark matter distribution in the primordial universe, influencing how scientists interpret its gravitational influence on galaxy growth. Furthermore, advanced observations of this distant galaxy could shed light on the mysterious epoch known as cosmic reionization, when radiation from the earliest stellar populations and active galactic nuclei stripped electrons from neutral hydrogen atoms, fundamentally altering the transparency of the universe. Given its luminosity and rapid star-forming activity, HLSJ091828.6+514223 might have played a significant local role in driving reionization processes, illuminating and transforming its surrounding intergalactic medium at unprecedented speed and scale. Studying its ultraviolet and infrared emissions might help astronomers pinpoint the specific stellar populations responsible for this pivotal cosmological transition. Scientists are also investigating whether galaxies like HLSJ091828.6+514223 represent a crucial missing link in the evolutionary history of massive galaxies observed closer to home. Could early, hyperluminous starburst galaxies rapidly evolve into the massive elliptical galaxies observed in today's mature universe, with their dense cores and aged stellar populations? If so, this distant object might offer crucial insights into the initial conditions and processes that produced some of the largest and most massive structures known. Recent theoretical work speculates further on how such galaxies impact their broader cosmic environment. The powerful stellar winds and radiation pressure from these early, intense star-forming regions likely propelled metal-enriched material outward into intergalactic space at immense velocities, triggering chemical enrichment far beyond galactic boundaries. Such interactions would have profound consequences for subsequent generations of galaxy formation, potentially altering cosmic chemistry on scales never previously imagined. By pursuing multi-wavelength analyses, from X-ray to radio, astronomers will further decipher the physical mechanisms fueling this galaxy's rapid evolution. Such comprehensive approaches will help distinguish between competing theoretical explanations. Was it intense starburst activity alone, or did interactions with nearby protogalactic companions amplify this extraordinary growth? Or was there indeed a hidden, rapidly accreting supermassive black hole orchestrating these extreme conditions? In the cosmic tapestry revealed by HLSJ091828.6+514223, astronomers glimpse more than a single anomaly. They encounter a profound invitation to revise and enrich our cosmic narratives. Each new piece of observational evidence demands adaptation, refinement, and sometimes reinvention of foundational theories about how complexity and structure emerged from the universe's primordial simplicity. Far from undermining cosmological science, objects like HLSJ091828.6+514223 stimulate innovation, prompting theorists and observers alike to venture boldly into the unknown, continually redefining humanity's understanding of the universe and our place within it. As the story of HLSJ091828.6+514223 unfolds, it also invites profound questions about the chronology of the cosmos itself. If such complexity, rich in dust, metals, and turbulent star formation, existed so early, then perhaps the timeline of cosmic evolution is more compressed than previously believed. Instead of a slow, stepwise build-up from simplicity to structure, we may be looking at a universe that rushed headlong into maturity, with pockets of accelerated evolution emerging mere hundreds of millions of years after the Big Bang. This idea is gaining traction in part due to statistical anomalies revealed by deep surveys, galaxies that should not exist at their observed redshifts because they are too massive, too dusty, or too chemically evolved for their epoch. HLSJ091828.6+514223 is not alone. It is part of a growing population of early universe outliers that, taken together, hint at a more chaotic, nonlinear birth of structure. A cosmos of unexpected richness, where the seeds of future galactic giants were planted in turbulent, overdense regions that defied the average behavior of the young universe. Some of the more speculative models go even further, proposing that early feedback from black holes and massive stars may have triggered secondary waves of star formation, creating nested generations of stellar populations in record time. Others suggest a variable speed of star formation across different environments, with some regions evolving orders of magnitude faster than others, a cosmic patchwork of rapid and slow growers, driven by initial density perturbations left over from inflation. In this view, galaxies like HLSJ091828.6+514223 are not just anomalies to be explained, they are archetypes of an alternate cosmic rhythm, one that pulses faster, grows richer, and becomes structured far sooner than the smooth curves of classical models predict. Their discovery opens up entire new branches of inquiry. How early did galactic winds begin shaping the intergalactic medium? When did the first true molecular clouds form? How did the first galactic magnetic fields emerge and influence star formation? Each new observation acts like a core sample from the ancient cosmos, drilled from a time when the laws of structure formation were being tested to their limits. And with each spectrum, each image, each point of data, HLSJ091828.6+514223 speaks a little louder, not in the language of simplicity, but in a dialect of complexity, turbulence, and evolutionary speed. It tells us that the early universe was not a blank slate, it was already writing intricate, layered stories in gas, dust, light, and time. And we are just beginning to learn how to read them. This reading, of light stretched thin by the expansion of the universe, of spectra etched with the fingerprints of ancient elements, is reshaping our understanding not only of how galaxies formed, but of what the universe was capable of becoming, even in its youth. HLSJ091828.6+514223, glowing cold and bright from the edge of the observable cosmos, defies the neat progression outlined in standard models. It urges us to consider that evolution, both cosmic and biological, may proceed not in smooth gradients, but in sudden leaps, punctuated by extreme environments, violent interactions, and rapid bursts of transformation. This galaxy is not merely an astrophysical curiosity, it is a fossil of intensity. A relic of a universe that moved quickly, collapsed early, and built complexity with urgency. Its very existence suggests that the conditions for making stars, metals, molecules, and perhaps even planets, emerged far earlier than textbooks once claimed. The icy grains detected in its interstellar medium are not only chemical residues, they are cosmological signatures, whispering that the architecture of later planetary systems might have roots deeper in time than we dared imagine. If such galaxies were widespread, the implications would ripple far beyond astrophysics. A faster chemical enrichment of the cosmos implies earlier habitable zones, earlier complex molecules, and perhaps even earlier biological possibilities. The boundary between cosmology and astrobiology begins to blur. What if the window for life to emerge opened not billions, but hundreds of millions of years after the Big Bang? And yet, for all its revelations, HLSJ091828.6+514223 also remains a question. A question flung across 13 billion light-years. It challenges us to refine our instruments, to sharpen our models, and above all, to listen carefully to what these early galaxies are trying to tell us. They are not echoes of simplicity, but heralds of sophistication. Not the prologue of a long, slow epic, but the opening movement of a cosmic symphony that began more violently, more beautifully, and more rapidly than we once believed. And perhaps, somewhere in that ancient, icy light, there is also a message about ourselves, that complexity is not a final destination, but a response to pressure. That beauty can arise not from equilibrium, but from turbulence. That even in the coldest corners of time, galaxies found a way to ignite. And so we continue to watch, to listen, to calculate, and to marvel. We marvel not just at the brilliance of a single galaxy, but at what it reveals about the fabric of reality itself. HLSJ091828.6+514223 stands as a testament to the idea that the universe is not only older than we can grasp, but deeper, more layered, and far more volatile in its infancy than once imagined. It embodies a paradox, an icy galaxy ablaze with star formation, a young structure, ancient in chemical richness, a snapshot from the past that accelerates the future of our understanding. Every photon it emits carries a story from a time when the cosmic background was still warm, when the first filaments of the cosmic web were tightening, and when gravity had only just begun its great sculpting of the universe. Yet from that era, where we once expected silence and shadow, we see instead a burst of complexity. This is a galaxy that should not be, and yet it is. Its cold dust radiates in millimeter waves, its molecules vibrate with unexpected precision, and its gravitational structure hints at an invisible architecture of dark matter more intricate than models predict. It is as if the galaxy knew how to self-organize before the textbooks allowed it, assembling stars, forging elements, weaving dust and gas into luminous structure under the direction of forces we're only beginning to decode. And this brings us to one of the most exhilarating implications of all: what else are we missing? If galaxies like HLSJ091828.6+514223 are more common than we thought, simply hidden by the limitations of our instruments, then the early universe may be teeming with complexity yet undiscovered. With every advance in telescope sensitivity, every refinement of lensing techniques, we peel back another layer of that ancient veil. We begin to see not a dark age, but a dawn bursting with unexpected light. The cosmos is not a passive stage on which matter slowly organizes, it is a restless engine of emergence. HLSJ091828.6+514223 is a spark from that engine, a relic that confounds, a signal from a time when the rules were written in turbulence and density, not order and calm. It speaks to a universe that prefers not perfection, but possibility. A universe that, even in its earliest chapters, was already dreaming in stars. And perhaps that is the most profound realization of all, that the universe, from its very beginnings, was not merely a canvas of expanding space, but a storyteller, a cosmic author capable of expressing complexity, contrast, and contradiction from its very first pages. HLSJ091828.6+514223 is one such chapter. A page torn from a time when galaxies should have been fragile, dim, and chemically barren, but instead we find something bold, luminous, and rich with the dust of forged elements. Dust that will someday become the soil of planets, the skeletons of life, the memory of stars. This galaxy doesn't just challenge our understanding of astrophysics, it expands the emotional scope of cosmology itself. Because in it, we witness something deeply familiar: resilience. It is a system shaped not by ease, but by extremes. Bombarded by gravity, stretched by motion, scarred by radiation, and yet, it builds. It remembers. It glows. What emerges is a poetic symmetry, that the cosmos, like consciousness, is capable of bending without breaking. Of spiraling into new forms under pressure. Of creating something elegant from chaos. The study of HLSJ091828.6+514223 will continue, its dust will be modeled, its spectra dissected, its emissions mapped across wavelengths. But even as the data flows and the theories adapt, one truth endures: this galaxy has already changed us. It has deepened the timeline of what is possible. It has reminded us that the early universe was not a silent void waiting to be filled, but a kinetic field of emergence, already bursting with structure, already echoing with creation. And so we look further. Not just to confirm what we know, but to be surprised again. To find, in the distant cold, a spark of fire. In the earliest light, a hint of memory. In the farthest galaxy, a reflection of what it means to form, to evolve, not despite the pressure, but because of it. HLSJ091828.6+514223 still turns, still shines, still sends its frozen music across the abyss. And we, here on a tiny world made of similar dust, are just beginning to hear the song. Of course. Hey, race a long, continuous, poetic and scientific expansion of the narrative, keeping the same tone of awe, depth, and intellectual beauty, dedicated to HLSJ091828.6+514223, the icy galaxy, born in fire. From the edge of visibility, across 13 billion years of expanding silence, a cold whisper reaches us, not in words, but in submillimeter waves, in the glow of ancient dust, in the fractured light of a galaxy that should not exist. HLSJ091828.6+514223. An astronomical designation, sterile on the surface, yet beneath it lies a story that redefines the infancy of the cosmos. This is not just a distant galaxy, it is a paradox in motion. A beacon of contradiction. It exists in an era where the universe was scarcely 700 million years old, a time when darkness still clung to the cosmic web, when the first stars were just beginning to carve complexity into the void. And yet, this galaxy pulses with dust. With metals. With water vapor and carbon monoxide. With ingredients that, according to our theories, require time for stars to be born and die, time for supernovae to enrich the interstellar medium, time for molecular clouds to cool, collapse, and coalesce into the luminous architecture of galaxies. But HLSJ091828.6+514223 didn't wait. It rushed into being. It challenges the timeline, questions the models, and pushes against the boundaries of what early galaxies are supposed to be. In a cosmos still trembling from its own birth, this galaxy is already building, already burning, already remembering. Infrared observations reveal that it produces stars at rates hundreds of times faster than the Milky Way, an inferno hidden beneath a mask of cold. The submillimeter radiation, captured by ALMA and other instruments, paints a picture of a galaxy wrapped in thick veils of dust, like embers buried in ash. It is a galaxy simultaneously obscured and illuminated. A cosmic contradiction. An icy galaxy that radiates with fire. Its very existence implies that processes we thought took billions of years may, under the right conditions, unfold in mere hundreds of millions. It implies that gravity, if concentrated enough, can condense the raw materials of a complex galaxy in a flash of cosmic time. That the first supermassive black holes, those titanic engines of light and shadow, may have formed not gradually, but violently, and earlier than we dared consider. It forces us to reimagine the early universe, not as a slow dawn, but as a thunderclap. Perhaps this galaxy formed at the intersection of colliding streams of gas along filaments of the cosmic web, massive rivers of hydrogen pouring into dense dark matter wells. Perhaps it devoured smaller protogalaxies, consumed their stars and dust, igniting starbursts and triggering feedback loops of furious creation. Or perhaps it harbors a quasar at its core, hidden behind dust, feeding a black hole millions or even billions of solar masses in size, pulling matter inward, unleashing jets, reshaping space and time around it. We do not yet know. But what we do know is this: HLSJ091828.6+514223 is not a silent relic. It is a challenge. A crack in the framework. A sign that the early universe was more chaotic, more fertile, and more capable of miracle than our models had room to imagine. And it reminds us, perhaps most beautifully, that the universe is not bound by the pace we assign it. That even in its coldest regions, under pressure and shadow, it can burst forth with brilliance. That it does not wait for permission to create complexity. Dust, ice, light, time. This galaxy tells us that these are not separate things. They are the same thread, spun together by gravity, by chemistry, by collapse and explosion and collapse again. They are the language of structure, the memory of stars, the possibility of planets. When we look at this galaxy, we are looking at the raw ingredients of everything we know: carbon for the bones, oxygen for the breath, iron for the blood. These elements were born in fire, scattered in death, and cooled in the silence of space, only to be reignited in galaxies like this one. So what else lies beyond the veil? What other galaxies were born too early, shining too bright, hiding in the fog of cosmic infancy? The James Webb Space Telescope is already beginning to answer this question. And with every ancient photon it collects, it brings us closer not just to the past, but to a new kind of future. One where the laws of cosmic evolution are rewritten not by dogma, but by discovery. Where galaxies like HLSJ091828.6+514223 are no longer exceptions, but the beginning of a new understanding. Perhaps we have misunderstood what it means for something to be young in the universe. Perhaps age is not measured in years, but in intensity. In the depth of memory etched into matter. In how quickly a system learns to build, to shine, to leave a mark on the fabric of space-time. If that is true, then HLSJ091828.6+514223 is ancient, not in chronology, but in significance. A survivor of gravity's most primal experiments. A monument to cosmic urgency. A galaxy born not in peace, but in pressure. And we, orbiting a modest star on the edge of a quiet spiral, are its witnesses. We have heard its light. We have read its dust. And in doing so, we have seen, if only for a moment, what the universe is capable of becoming, when it does not wait. We often imagine the early universe as simple, a cold lattice of hydrogen, drifting in the afterglow of the Big Bang, awaiting the slow unfolding of time. But galaxies like HLSJ091828.6+514223 rise like contradictions, like whispers from a different creation. They tell us that the early cosmos was not patient. It was not clean. It was not empty. It was restless, chaotic, fertile. Already carving structure from collapse, already breeding the seeds of starlight beneath veils of darkness and distance. At a redshift of nearly 6, when space was still filled with neutral hydrogen and cosmic dawn had barely begun, this icy flame of a galaxy was already alive. Not dormant, not building gradually, but in bloom. Its cold dust glows with infrared brilliance, revealing molecular complexity that should not yet exist. Its interstellar medium, laced with carbon monoxide and water vapor, speaks of cycles of birth and death. And yet it had no time to wait for death. The stars must have come fast. Massive. Furious. Dying young. Enriching the galaxy not in slow epochs, but in supernova storms. In waves of enrichment that seem to compress time itself. Theoretical models strain to contain such galaxies. In most simulations, heavy elements take time to accumulate. Dust takes time to form. Starburst phases take time to ignite. But HLSJ091828.6+514223 doesn't fit. It hints at a universe with flashpoints, zones of gravitational excess, of extreme inflows, of early mergers and dark matter halos that collapse like traps, pulling matter inward with such force that time seemed to bend around them. The birth of complexity, condensed. And with it comes the question, what are we missing? How many galaxies have we not yet seen, lying hidden behind dust or diluted into background noise? How many early systems defy the smooth, clean evolution plotted in textbooks and graphs? Each discovery like this is not just an observation, it's an excavation. A piece of deep cosmological memory uncovered. A fossil glowing not with age, but with possibility. What's more, HLSJ091828.6+514223 forces us to confront a more intimate idea, that complexity doesn't always need time, it needs tension. It needs imbalance. It needs the asymmetry of pressure and collapse. Perhaps, in the most compressed corners of space, the laws of emergence rewrite themselves. Perhaps time flows differently in the presence of such density. Perhaps star formation, under the right conditions, is not a gentle process, but a detonation. There is beauty in that violence. Because this galaxy is not just matter, it is narrative. Its dust is not debris, but documentation. Each element present, oxygen, carbon, silicon, is a signature of an event. A thermonuclear explosion. A gravitational collapse. A fusion chain that ended in light. These atoms did not exist at the moment of the Big Bang. They were made in stars. Which means the stars were already there. Which means this galaxy has memory. And what is memory, if not structure built from the past? Astronomers today look at HLSJ091828.6+514223 and see a question mark hung in infrared. They ask, how did it form? Was it the result of a rapid collapse along a filament of dark matter? Was it a merger of smaller halos, an early collision that sparked runaway starbirth? Or was it centered around a primordial black hole, one of the earliest titans, gathering mass so quickly that it dragged the galaxy into premature brilliance? Every explanation leads to more mystery. Every observation adds complexity. But this is not failure, this is expansion. Science thrives not on answers, but on better questions. And this galaxy, this cold bright wound in spacetime, asks one of the best, what if the universe was ready before we were? What if the first galaxies were not delicate structures, forming like crystals over billions of years, but wild storms of gravity and gas, roaring into light? What if the cosmic dark ages were not silence, but gestation? Perhaps this galaxy is not the exception. Perhaps it is the rule, and everything else is delay. And so we must revise. Rethink. Resimulate. The cosmological models must now include turbulence. Bias. Local pockets of overdensity where evolution accelerates. Where feedback loops tighten. Where stars form, explode, and seed the next generation in a chain of causality too fast for prior algorithms to track. And what does this mean for the history of everything? It means planets may have formed sooner than expected. It means the chemical conditions for life, organic molecules, carbon chains, water ice, may have existed not 5 billion years ago, but 12. In places we cannot yet see. In systems that vanished long before Earth was born. It means the potential for life did not arise late, it could have arisen early. In the very dawn. In the glow of galaxies like HLSJ091828.6+514223, whose dust now drifts through the intergalactic medium, cooling, combining, waiting. It is humbling. And it is beautiful. Because in this one frozen galaxy, we see not only the mechanisms of astrophysics, but the poetics of time. A reminder that in the universe, as in life, the extraordinary often appears where we least expect it. In the cold. In the young. In the silent shapes dancing at the edge of observation. And as our instruments sharpen, as telescopes like JWST peer further and deeper, we are likely to find more of these impossible galaxies. Each one a new stanza in the epic of cosmic genesis. Each one a contradiction. A challenge. A spark. The universe does not explain itself. It reveals itself, in pieces. And HLSJ091828.6+514223 is one such piece, radiant, impossible, enduring. A frozen fire. A cold storm. A galaxy made not just of matter, but of mystery. And it still spins, silently, at the edge of time. Absolutely. Here is the next poetic scientific continuation, further expanding the mystery and meaning of HLSJ091828.6+514223, while staying true to the tone of cosmic depth, philosophical resonance, and scientific curiosity. It still spins, silently, at the edge of time. And yet, though billions of years and light-years separate us, the presence of HLSJ091828.6+514223 is not distant. It is immediate. It bends the present. Alters how we interpret the past. Rewrites the scale on which we measure cosmic possibility. For what we're truly seeing, what we're always seeing when we look at such distant light, is not the past, but the persistence of the past. The refusal of early matter to remain formless. The insistence of gravity, chemistry, and chaos to assemble something meaningful in the earliest hours of existence. This galaxy, radiant beneath veils of ice and dust, tells us that the universe is a place where structure is inevitable. Not rare. Not fragile. Inevitable. Given the raw materials, the laws of physics will always lean toward formation, toward heat, toward complexity, toward light. Even in the cold. Even in the dark. Even when there hasn't been enough time. Time, it turns out, is not the only ingredient. Tension matters more. Density. Imbalance. Collapse. That's the hidden lesson of HLSJ091828.6+514223. That creation is not a process of equilibrium, but of disequilibrium. Things form not when the universe is calm, but when it is stressed. When matter is compressed. When energy is uneven. It is in the stretch, the imbalance, the asymmetry, that galaxies are born. And isn't that true beyond astrophysics? In the tension between what is and what could be, something new arises. So, in the shrouded depths of this galaxy, we see ourselves. Not literally, but metaphorically. We, too, are made of dust. We, too, are built from violence and memory. Every atom in our bones once belonged to a star like those burning within this frozen galaxy. Every cell in our bodies owes its chemistry to explosions that happened billions of years before Earth existed. We are not separate from this galaxy, we are downstream from it. We are its echo. Its descendants. And now, we point instruments back through the tunnel of time, and we see the origin of origins, not as a myth, but as light. As data. As shape and temperature and motion. We see the physics of our ancestry glowing faintly in the submillimeter sky. But there is more. Because this galaxy, for all its luminosity and irregularity, may still be hiding something deeper. What if at its core spins not just a cluster of stars, but a black hole, a colossus, ancient and hungry, forming at the very limits of possibility? If such a black hole exists in HLSJ091828.6+514223, it would demand an even more radical rethinking of the early universe. How could something so massive form so fast? Did it collapse directly from a cloud of primordial gas? Did it feed through cold accretion, drawing in rivers of intergalactic material at relativistic speeds? Or did it ride the shockwave of the first generation of stars, population 3 titans, that lived short, furious lives and left behind singularities so massive they became the seeds of monsters? We don't know yet. But we are learning how to ask. That is the gift of this galaxy, not just its spectacle, but its questions. Every beam of light from HLSJ091828.6+514223 has taken 13 billion years to arrive. And when it finally reaches the mirrors of our instruments, it does more than illuminate, it complicates. It forces the universe to be deeper than it was yesterday. This is the real work of science, not simplification, but enrichment. To encounter a galaxy like this is to watch knowledge unfold, not in neat conclusions, but in new layers. New questions. New structures of uncertainty. And still, the galaxy spins. Still, it burns. Still, it writes its frozen symphony across the sky, waiting not to be solved, but to be understood. Not to be conquered, but contemplated. Because in the end, HLSJ091828.6+514223 is not just an astrophysical object. It is a mirror. A message. A monument to the fact that the universe, even in its youth, was already fluent in wonder. Already capable of creating galaxies too strange to fit, too luminous to hide, too early to forget. And so we remember. We carry its light in our telescopes, in our theories, in the language of equations and awe. We chart its dust not just to map where it is, but to understand where we are. And we listen, quietly, reverently, to the song it sings. A song of collapse. Of becoming. Of complexity rising from cold. A song we are only just beginning to hear in full. Of course. Let us continue, deeper into the mystery, into the philosophy, into the silence between stars. Race the next extended part of the poetic scientific narrative, without pause, still centered on HLSJ091828.6+514223, and what it reveals not only about the cosmos, but about existence itself. And we listen, quietly, reverently, to the song it sings. But this is not a song composed of melody. It is a harmony of forces. A resonance of gravity and radiation. A rhythm of time stretched and space curved. This galaxy is not music in the way we know it, but in the way the universe knows itself. Through pattern. Through recurrence. Through structure emerging from chaos. Somewhere within it, cold clouds of gas once began to fall inward, slowly at first, then rapidly, then unstoppably. Pressed by their own mass. Compressed by their own silence. And from that pressure, fusion was born. Starlight. Heat. Ultraviolet light piercing the dust, scattering against molecules, reshaping the chemistry of everything nearby. From silence, fire. From darkness, form. From nothing, memory. For this galaxy is ancient not because of its age, but because of what it holds. Its dust contains secrets, the ratio of metals to hydrogen, the temperature of its star-forming regions, the spectral signatures of molecules that are the precursors of life. It is an archive, written in dust instead of words. In photons instead of ink. And we, with our fragile machines, telescopes balanced in orbit, arrays of radio dishes on distant plateaus, have become its readers. We decipher its language. We measure its light. We model its gravity. And still, it surprises us. We find turbulence where we expected stillness. We find maturity where we predicted youth. We find echoes of processes so fast, so violent, that they should be impossible under our current understanding of time. And so, our models evolve. Our timelines shift. We extend the boundaries of possibility back toward the beginning. We begin to suspect that the cosmic narrative we thought we understood, the neat sequence of reionization, metal enrichment, galactic formation, may have been far more nonlinear than we imagined. Maybe the early universe wasn't quiet at all. Maybe it was an arena of explosions. A furnace of gravity. A theater of acceleration and transformation. Where galaxies like HLSJ091828.6+514223 were not anomalies, but early protagonists. Carving complexity from nothingness. Condensing stardust from primordial plasma. And as we update our simulations, as we adjust the parameters to match what we now observe, we realize something deeper: the universe did not wait for us to be ready. It simply was. It became. It continues becoming. And perhaps that's the most profound message hidden in this frozen, luminous galaxy. That the universe does not progress toward perfection. It spirals toward expression. Not symmetry, but signature. Not order, but identity. Every galaxy is different. Every merger, every collapse, every magnetic field and gas flow creates a unique fingerprint. And this one, this icy fire drifting near the edge of the observable cosmos, is no exception. It is singular. It is unrepeatable. It is a testament to cosmic individuality. And yet, it shares its essence with us. Because we, too, are processes of compression. Of collapse and light. We are not separate from the forces that shaped HLSJ091828.6+514223. We are descendants of them. Our atoms were born in places like this. Our chemistry was written in the first stars. Our minds, our thoughts, our very capacity to wonder, are products of ancient nuclear reactions in galaxies too distant to touch. And that is why we look back. Not only to understand the cosmos, but to understand the conditions that made knowing possible. We are the only species we know of that can ask what a galaxy is, and that question is a legacy of the galaxies themselves. Their stars made us. Their dust seeded us. Their silence invited us. And now, their light has reached us. After 13 billion years, this single galaxy, obscured, distorted, stretched by the expansion of space, still speaks. Not with answers, but with invitation. To look deeper. To think harder. To feel smaller, and more connected. To understand that even at the edge of visibility, there are voices waiting to be heard. And in the frozen spirals of HLSJ091828.6+514223, we hear one of them clearly. I existed when time was young. I built stars in a sea of nothing. I forged dust from death. I survived the dark. And I still shine.